Hello. Again, we're going to do a quick overview of proton NMR because, again, this is a PowerPoint that you should have done in lab with your instructor. All of the slides are in your spectroscopy workbook, so you can work through this and look at all of the examples. We're just going to hit the highlights today. So we're going to look at the data that you can get from a proton NMR. Much like carbon-13 NMR, we're going to get the number of unique hydrogens and chemical shift. But unlike carbon-13 NMR, we're going to get two more pieces of information, the integration and the multiplicity. I'm going to go through these very quickly. So let's do that. So number of unique hydrogens, we're going to do the same thing as we did with pentane in the carbon-13 NMR. I have a plane of symmetry that heads through this molecule, even though it will look, yep, there we go, there's that hydrogen. This kind of looks like it's not symmetric, but remember the chlorine's pointing toward me and the hydrogen's pointing back in the same plane. So the two methyl groups here are identical. These two CH2, the two hydrogens here are identical in red. And then this green one is its own, so 3 peaks. But make sure when you're looking for these that you look for hydrogens that aren't drawn in to make sure you're counting those when you're looking for predicting the number of peaks. So this would have 3 peaks. Chemical shift also is very similar to carbon-13 NMR, except instead of 0 to 220, we're doing 0 to 14. But it's the same idea that here it's about halfway here, around 4, 4.5. We're split in half where it's mostly sp3 down here and sp2, just a generalization. sp2 above, sp3 below, so geometry matters, and so does the dipole. More electronegative atoms will impact how positive a hydrogen feels, and it will move it further downfield. So let's see, I think, yep, here we go. We can even compare them with the carbon-13. So sp3 carbons bonded only to carbon and hydrogens below 40, here below 2. 40 to 70 or 80, carbon to an oxygen, carbon to a nitrogen, carbon to a bromine, same thing in the proton NMR, just 2 to 4. sp2 alkenes and aromatics range from really about 120 to 160. You didn't see them much below that. And here we see them from about 4.5 to about 8. Okay, so maybe 5 to 8. And we have them separated out. Carbon alkenes tend to be more like 5 to 6, and aromatic rings are 6 to 8. And then aldehydes show up because this has a proton on it. Ketones don't show up, they don't have a hydrogen on them. So ketones and aldehydes show up at 220. Acids, esters, amides, acid chlorides show up between 160 to 180. Here, acids show up between 12 to 14, aldehydes 10 to 12. And there's some overlap in these. The other piece of information to remember is deuterated chloroform has a little bit of CHCl3 in it. And that shows up at 7.24 in the proton NMR and at 77 in the carbon-13 NMR. Again, I want to remind you that there's Quizlets that are linked in the Canvas page. So you can go in there and memorize these regions. You don't have to know every single little detail, but you should know about 6 regions for carbon and about 6 regions for proton NMR. And it'll make the interpretation so much easier. Okay, then we have 2 pieces of data that you don't get from carbon-13 NMR. Integration. And integration is the number of hydrogens observed in that peak. And there are 2 different ways that you might see this, or 3. Often you'll see it as this stair step. And then you can measure this height of this stair, and then you take that and say, what is the ratio to this next one? And if I had a ruler, I would say, okay, there's 2, and this is close to 3, and I didn't do it very carefully. 3 hydrogens. So this is a 1 to 3 ratio, and if I split this in half, that's 1 to 3. Or if you prefer, it's 6 to 2. So this peak has 2 hydrogens, and this peak has 6, because it's a ratio. So 6 to 2 is the same in the integration as 1 to 3, and you can't tell them apart. So you won't know until you start to figure out more of the structure, whether you really have 2 to 6 or 1 to 3. Sometimes you'll just get the number, and that makes it super easy. You don't have to interpret it. And on your spectra, you'll get this stair step, but the computer will integrate it for you, and you just have to normalize, pick which one you think is 1 hydrogen, and it'll tell you what the ratio is to the other peaks in the spectrum. So then here's another example. And then this one just says this one is measured in millimeters. So we went in with a ruler, 25 to 10 to 25. So we could say 25 to 10 to 25, but so that's certainly a ratio that would work. 2 to 1 to 2 doesn't work, because this would be 2.5 to 1 to 2.5. But if I divided them all by 5, 5 to 2 to 5 works. So either one of these are possible. And then the last piece of information is the multiplicity, which we also usually make sure we don't see in the carbon-13 NMR. And that is the number of lines in each peak. So you could have a singlet, and that tells you the number of hydrogens on the carbon next door. The integration tells you the number of hydrogens on the peak you're observing. So this one would be an integration of 1, but there are no hydrogens next door, so it's a singlet, 0 hydrogens on these carbons, because they're all quaternary. This one is a peak that looks like a doublet, a 1 to 1 ratio. That means there's 1 hydrogen, so this is who we're observing, this is the integration, and there's 1 hydrogen next door. So blue is who's being observed. The multiplicity tells you how many it sees. How many hydrogens does the blue one see? So we could go either direction. This way is a +1. So this is who's being observed. There are 2 next door. So this sees 2 +1, I'll see a triplet. If I'm going from here to this, I subtract 1. So if I see a triplet, I know there are 2 hydrogens next door. If I see 2 hydrogens next door, I know it's +1 and it's a triplet. So make sure you practice the directions. This is also in that Quizlet on NMR spectroscopy. So practice some of these interpretations. If you have a quartet, there is, if you're this CH2, you'll see 3 hydrogens next door. If you're this CH2 and you see 3 hydrogens, it's a +1, it's a quartet. So you have, this is repeating the same thing. You have 4 pieces of information. Number of peaks, you have the chemical shift, so what's bonding to it, is it downfield or upfield? Electronegative atoms, double bonds. How many protons are observed on that peak, and how many are next door, which allows us to start to put full structures together. So go through, there's some practice problems in the online book, also some links to websites where you can practice this. And then in the next video, we go through and start making data tables so we can start drawing partial structures and interpreting these. And there'll be those opportunities to keep practicing interpretation. So good luck, this is fun, but it takes some practice.